Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic, we're going to discuss three inequalities about complex numbers. So in this topic, we will begin by describing the idea of a monotonic increasing function. We will then use this idea to prove three inequalities about complex numbers. Now, for real numbers, you are already aware of this property. Theorem: for any real number x, x is less than or equal to the absolute value of x. Proof: well, reasonably straightforward. Let's look at the two cases. If x is greater than or equal to 0, then by definition x is equal to the absolute value of x. Now, 0 is less than or equal to the absolute value of x, as the absolute value of x is always positive. And if x is less than 0, then x is less than 0, which is less than or equal to the absolute value of x. Consequently, by transitivity, x is less than the absolute value of x. Therefore, we have two and only two possibilities. Either x equals the absolute value of x, or x is less than the absolute value of x. Consequently, the above statement must be true. X must be less than or equal to the absolute value of x. We indicate the end of a proof by a solid white rectangle. Now, a real valued function f of a real variable is said to be monotonic increasing on the interval ab if the value of f at x1 is less than or equal to the value of f at some point x2 whenever x1 and x2 are between a and b and x1 is less than or equal to x2. So basically what this says is if you evaluate the function at one point x1 and move a little bit to the right, you are guaranteed that the value of the function can only be increasing. Now, theorem: a differentiable real valued function f of a real variable is monotonic increasing on the interval a to b if and only if the derivative of f is greater than or equal to 0 for all values of x between a and b. All right. The proof of this is a consequence of the mean value theorem from calculus, which if you haven't seen, you will see in the upcoming months. But it's a simple way of just observing that a function is monotonic increasing on a particular interval. Now, examples of monotonic increasing functions with their corresponding intervals are shown here. For example, x squared. The derivative of x squared is 2x, and 2x is greater than or equal to 0 whenever x is greater than or equal to 0. Similarly, the square root of x is defined for values of x greater than or equal to 0. And on that interval, the derivative is defined as 1 over 2 times the square root of x. So on that interval, apart from 0, the derivative is strictly greater than 0. Ln of x has a derivative of 1 over x on the interval from 0 to infinity, and 1 over x is positive on that interval. And so ln of x is monotonic increasing for all positive values of x. Now, x cubed, on the other hand, its derivative is 3x squared. 3x squared is positive for all real values, and therefore x cubed is monotonic increasing for all values of x, and the same with e to the x. The derivative of e to the x is e to the x, and e to the x is greater than 0 for all real numbers. We are going to define the interval where the function is monotonically increasing as the domain of monotonicity. All right, so if I have a sequence of points in order, all of which lie on the domain of monotonicity of the function f, then it automatically follows that f evaluated at the first point is less than or equal to f evaluated at the second point, and so on and so forth up until that last value. In this course, we are generally going to use this property as follows. If 0 is less than or equal to x, which is less than or equal to y, then 0 is less than or equal to x squared, which is less than or equal to y squared. Similarly, we can say the following. If 0 is less than or equal to x, which is less than or equal to y, then 0 must also be less than or equal to the square root of x, which itself must be less than or equal to the square root of y. Here is our first inequality. Given a complex value z, the real part of z is less than or equal to the absolute value of the real part of z, which is less than or equal to the absolute value of z. Proof. Well, because the real part of z is a real value, it follows from the previous theorem that the real part of z is less than or equal to the absolute value of the real part of z. So that immediately follows from the theorem we discussed at the start of this topic. Now, if z is equal to alpha plus beta j, then because beta squared is greater than or equal to 0, it follows that alpha squared must be less than or equal to alpha squared plus beta squared. So alpha squared is greater than or equal to 0, and because beta squared is also greater than or equal to 0, if I add beta squared to the right-hand side, it must be greater than the left-hand side. Therefore, by monotonicity, it follows that the square root of the left-hand side is less than or equal to the square root of the right-hand side. But wait a second. The square root of a real value squared is just the absolute value of that value, and that happens to the real part of z, and the right-hand side is the absolute value of z by definition. So, therefore, the second half of this inequality is proved. Next, given a complex value z, the imaginary part of z is less than or equal to the absolute value of the imaginary part of z, which is again less than or equal to the absolute value of z. Well, this proof is left to you, the viewer. Now, suppose I told you that for two real numbers x and y, the absolute value of x and y are both less than 10. But the absolute value of the sum is 1368. You probably wouldn't believe me. In fact, if I told you that the absolute values of x and y are both less than or equal to 10, but x plus y has a magnitude of 20.1, again, you probably wouldn't believe me. Because after all, if x and y are as large as they could be, which is 10 and 10 respectively, the largest value that would be is 20, which is less than 20.1. In a sense, you already understand the following theorem. Given x and y as real numbers, then the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. That is, the sum cannot be greater than the parts. Proof. Well, let's start with x plus y all squared. Well, okay, that's easy enough. We can square that out, expand it, and we get x squared plus 2xy plus y squared. Now, the x squared is equal to the absolute value of x all squared, and from the previous theorem we saw that 2 times x times y is less than or equal to the absolute value of 2 times x times y. And the same, y squared is equal to the absolute value of y all squared. So let's substitute all of that in. Okay, next. The absolute value of 2 times x times y is the absolute value of 2 times the absolute value of x times the absolute value of y. And because 2 is already positive, we can just evaluate it as being 2. So now the absolute value of 2 times x times y is twice the absolute value of x times the absolute value of y. All right, let's substitute that in. Oh, but wait a second. This is just the absolute value of x plus the absolute value of y all squared. All right, so the first term equals the second, which is less than or equal to the third, which equals the fourth, which equals the last. Therefore, the first is less than or equal to the last. And both of those values are positive. Because they are both positive and the square root function is monotonic, it follows that this statement is indeed correct. However, wait a second, the left-hand side is by definition the absolute value of x plus y. On the right-hand side, I have the absolute value of the absolute value of x plus the absolute value of y. But the absolute value of x plus the absolute value of y is already positive, so I can leave that as is. So because the sum of the absolute values is greater than or equal to 0, it follows that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Okay, nice. The same holds for complex numbers. So given w and z as complex numbers, then the absolute value of w plus z is less than or equal to the absolute value of w plus the absolute value of z. Let's prove that. Okay, so here's the proof. By definition, the magnitude of w plus z all squared is w plus z times the conjugate of w plus z. All right. Now you'll also remember that the conjugate of a sum is the sum of the conjugates. And so we'll bring the conjugate inside the second parenthesis. We can now expand this out. First, outside, inside, last yields w times w star plus w times z star plus z times w star plus z times z star. Now, that first value there is equal to the absolute value of w squared. Now, for the next value, note that the conjugate of the first term, wz star, is equal to that expression we see here, but the conjugate of a product is the product of the conjugates, so we will conjugate both the first and second term. So that gives us w star z double star. But the conjugate of a conjugate is the value itself, so this is just equal to w star z. And complex multiplication is commutative, so I can write it in the opposite order. Oh, wait a second. That says that the third term is the conjugate of the second term. You will recall that z plus z conjugate is twice the real part of z. Well, in this case, we have w times z conjugate plus its entire conjugate. Therefore, the sum of those two values is twice the real part of w times z conjugate. All right. Now, the third term is just the absolute value of z squared. All right. Now, from the previous theorem, we saw that the real part of a complex number is less than or equal to the absolute value of that complex number. So therefore, that entire expression is less than or equal to twice the absolute value of w times z star. Okay, and we know that the absolute value of a product of complex numbers is equal to the product of the absolute values. So I can do exactly the same thing. And the absolute value of z star is equal to the absolute value of z. And I think you can see where this is going. This entire expression is once again the absolute value of w plus the absolute value of z all squared. Because both the first term and the last term are strictly positive, or are greater than or equal to 0. After all, w and z may both be equal to 0. Therefore, we can take the square root of both of them to get that the square root of the left-hand side equals the square root of the last term, right-hand side. Oh, and wait a second. Same thing as before. What's under the square root on the left-hand side is already positive, and what's under the square root within the square is also positive. And thus, because both of those values are already positive, we just know that the absolute value of w plus z is less than or equal to the absolute value of w plus the absolute value of z. Nice. So, following this topic, you now understand the concept of monotonic increasing functions, and you know these three inequalities. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!